Hi there, my name is Skip Pomeroy. I'm a faculty member in the Department of Chemistry and Biochemistry here at UC San Diego. I'm going to talk to you today about the chemistry for bio-based materials. And you've heard a bunch of talks about algae and all the other things that are derived and we work on in production algae, but I sort of view them as little chemical factories that make molecules that we can then use and manipulate. And so you can see in the micrograph there the pictures of the Cenodesmus up close, but you can also see them in full-scale production. Then there are lots of different ways in which we process these chemicals into things for power mostly in the past, but we're also going to look at what other sort of molecules do they naturally sort of make, and one of those that you can see in the bottom middle panel is an extraction of the algae to get the lipids out. And it's those lipids that we can then convert into bio-based fuels like biodiesel, which you can see over on the bottom left-hand panel. The two young ladies there had the biodiesel layers in the top and the glycerol layers in the bottom. Or we can take those same lipid molecules and convert them into things called polyols, which are a base chemical used in making polyurethanes. And so we got two examples over on the bottom right, where we have rigid foam for surfboards and what's called an elastomer for making shoe soles, and then foams for the insoles. So the question now is, we're just going to review a little bit about how we chemically process these things. We can take the algae biomass and we can convert them either biochemically through direct combustion, in other words, just burn the algae, or we can do thermal conversions. And Mike Burkhart talked to you earlier about hydrothermal liquefaction and extraction, but if you look at all these different processes, what they're really all trying to do is to make either power directly or make molecules that are high in energy content to be used for the energy industry. And so that's an important part of where we've been processing algae in the past for energy. But what are the chemicals that really come out of algae? And so if we look at our two broad classes where we have microalgae, which are the single-celled organisms, or macroalgae, think the multicellular organisms, plants like kelp, you get hydrogen, lipids, and carbohydrates and along with the rest of the biomass. There's a class of molecules I've left out, proteins, and that's because they're not usually ever processed into anything else. The proteins are such high value items in and of themselves that those would be used for just protein value alone. But these base molecules can then be converted or interconverted into other molecules that can be used for both energy or for making renewable molecules to be used in the chemical industry. And so you can see that the hydrogen can be used along with the lipids to make what's called green diesel. Green diesel is renewable diesel that looks identical chemically to petroleum diesel. You can take carbohydrates and you can convert those as the black line and feed those carbohydrates to algae and make them into lipids, and then those lipids can be made directly into biodiesel, or they can be processed into the green diesel, right? Or they can also be made into other alcohols, and we'll talk about that in a little bit. The biomass can be made into syngas, which is synthetic gas, which can be used to make alcohols. Alcohols are important base chemicals in our world. From an alcohol, you can make just about any other chemical that you might imagine. You also make methane. The methane can be used directly for power generation, or you can use it in the process of what are called Fischer-Tropsch liquids, which are the ways that we can take and synthetically build up hydrocarbons into energy molecules by the Fischer-Tropsch process. We're going to focus on the lipids, okay? So what is a lipid? You also will hear the word oil or fats. Chemically, we refer to them as triacylglycerides. There is a glycerol backbone. You can see in the drawing on the right-hand side, the glycerol backbone is in black. And then there are three fatty acid residues, hence the tri part of triglyceride. And they're all attached to the glycerol through a series of links called ester links. That's the C double bond O link that goes into these guys. Now, I've shown you three different types of fatty acid residues. The one in the top, which is labeled R1. R is a typical thing that we substitute in for just these alkyl chains. And if it's a completely saturated alkyl chain, like the one in blue, R1, it's all a series of single bonds. Now, in that symbolism that you see there, every end of a line segment is a carbon. If it's not listed, it's a carbon atom. And then every carbon atom is assumed to have 4 bonds to it. So if there's no other bonds shown, those are bonds assumed to be to hydrogens. This just sort of simplifies the system. If there's a double bond, that's demarked by having two lines, and so you can see that in the green box and in the red box. These are unsaturated fatty acids, and we count them from the very first carbon, which is the carbonyl carbon. The carbon next to that is referred to the alpha carbon. You see that in the red box. And the very last carbon in the chain is called the omega carbon, also in the red box. Then we count over and we count where the double bond is located, and that's how we identify different sorts of fatty acid chains on these molecules. There's also another class of important molecules that are called the omega-3 fatty acids. So we go 3 carbons from the last carbon. If there's unsaturation there, that falls into this family of omega-3 fatty acids. These are important energy storage molecules, and that's why they make great molecules for deriving energy and power out chemically. But the one thing I want you to pay attention to right now, though, is these are really long, squiggly chains of molecules that can wiggle all over, but they get entangled in one another, so that when we go to look at things like viscosity, the viscosity of oils, and so think cooking oil, if you were to pour it out, its viscosity would be relatively high compared to something like milk. And that has an implication when it comes to making fuels. And so the fuel that we make from these lipids is biodiesel. Now, biodiesel is any bio-derived fuel that can go into a diesel engine. In principle, it could be the oil itself. And in Rudolf Diesel's original diesel engine, he did that by running it on peanut oil. But in today's definition, we want to go a little further because we want drop-in fuels. We don't want to have to modify the engines in order to run them. So biodiesel is any bio-derived fuel that can drop right into a regular diesel engine. Now, the biggest problem with these oils and why you have to undergo some sort of conversion is this viscosity factor. If you didn't match the viscosities better, then you'd have to change out the fuel pump and the fuel delivery system, and that's a cost that makes it impossible to use them back and forth between fuel sources. Some of the ways that we tried to get around this were by thinning the oils with water and alcohols and other things, and none of that really ever worked out very well. But in 1937, a Belgian chemist, Chavan, came up with a way of transesterifying these guys with methanol to create what are a class of molecules called fatty acid methyl esters. And so what we've taken, if you look at the inset box, is the large tag molecule where we've used the R1, R2, R3 just as the abbreviations for those long chains. We've attached a methyl group to the oxygen and removed them from the glycerol backbone. What this creates is 3 smaller molecules that are more linear in their chain formation, and so they tangle less, and their viscosities are very close to that of petroleum diesel. In fact, close enough that it can serve simply as a drop-in fuel. Now, what are the advantages of biodiesel? On top of the fact that, it's renewable and sustainable and biodegradable and non-toxic, the most important part is the reduction in global greenhouse gases. The source of the carbon is the atmosphere itself, unlike petroleum, which is where you're taking the carbon right out of the ground. So while we're combusting the fuel and we're going to have carbon dioxide come out of burning biodiesel, where that carbon came from in the first place was the atmosphere. So if you look at the graph on the bottom left, you can see if you look at diesel, we normalize diesel to be 100 and we compare everything to that. And if you look at all the technologies there, B100, which stands for pure biodiesel, not diluted in anything, right? That's the most carbon CO2, global warming gas, efficient molecule and process out there, even better than electric, because most electric cars derive their electricity from petroleum-based sources like coal. Now, the other thing that's important about biodiesel is that there's no sulfur in biodiesel. In petroleum diesel, we place sulfur in that fuel in order to give it some lubricity for the engine. This sulfur, though, when combusted, makes SO2, and this is a source of acid rain. If you look over on the right-hand graph, we see a bunch of molecules that are associated with combustion processes, and we're comparing petroleum diesel to B20 and B100. And what you see is B100 burns much, much cleaner, and that's mostly because it burns a lot hotter. And this results in fewer particulates, and these particulates are important from a health perspective because they serve as conveyors to bring other toxic molecules into our bodies. So it's about air quality, but it's also about your health. So Now I want to sort of switch gears a little bit and talk about another sort of chemical that you can derive from these lipids, which is a polyol, and we use it to make a compound called a polyurethane. Polyurethanes are plastics that are derived from reacting polyols with diisocyanates, and this is an enormous industry. This past year, it was over a $10 billion industry worldwide, where about 50% of that is in construction, where we use rigid foams for insulation, and in furniture. And so furniture is things like soft foams for mattresses and sofas. But there's also the electronics industry and the automotive industry that heavily use these things. That's about another third of the total polyurethane usage. And in the electronics industry, it's about insulation and getting coatings on things. And in cars, it's for the plastics and the seats inside the cars. Now, in addition to rigid foams and soft foams and making other sort of gaskets, there's another broad class of things that come out of here, which are called coatings, adhesives, sealants, and elastomers, sometimes abbreviated as CASE. And you can see examples there at the bottom. And you probably recognize names like Rust-Oleum and DAP, and you've probably used other sort of glues and polyurethane wheels as casters or skateboard wheels. And so this is an important base chemical that we use all over the world. So how do we make these polyurethanes? Polyurethanes are made by reacting a polyol and a diisocyanate to make a polyurethane, which is a carbamate ester. Now, a polyol is a molecule with multiple hydroxyl. Those are OH groups. And so what we want to do, if you can see that in the box on the upper right, you can see a molecule that's got two OH groups in it. And so that's our polyol. And then the one on the left is the isocyanate. Those then react together to create the bond that links the two molecules together. This is the urethane bond, which I've marked in red. And so what this is done for petroleum, and so the broad classes of polyurethanes, in between the oxygens and the urethane bonds, we can modify the carbon functions in there, and they're usually either polyethers, which are carbons linked directly with oxygens, or they're polyesters, which are carbons linked with the ester group C double bond O bond O. Bio-based polyurethanes are expected to have a huge impact on the global market and can be made from plant oils, and so that makes them renewable and sustainable. So what are these guys? And so they're referred to as natural oil polyols, or NOPs, and these can be used to make a large variety of base chemicals, from polyurethanes, polyolefins, polyamides, which is nylon, polyesters, and polyethers. Okay. They are much more efficient in terms of global greenhouse gases by 36%, and that's because the carbon source for these guys is coming out of the atmosphere. Okay. They use 61% less renewable energy. What people sometimes forget about is how much petroleum is used to do the heating that does the distillation in petroleum refining to break these things down and get them into their base chemical categories. And so altogether, you're looking at an overall 23 or about 25% less energy demand on you making these polyols from these natural oils. They're renewable, they're biodegradable, right? They're non-toxic, okay? And they can be made into a variety of ways. The beauty of plant oils is there's a large number of degrees of unsaturation, lots of double bonds, so those are lots of places where we can manipulate the chemistry. If you look over on the right-hand side, you can see an example of a polyol made from the tag that I've been using throughout this entire talk, and you can react it with a different isocyanate there, toluene diisocyanate, and you can see that typical inside the red box urethane bond. So what I hope I've been able to talk to you about a little bit is that we have an ability to make renewable, sustainable, and I'm going to argue biodegradable polyurethanes. And you've got three examples that we're working on here at UCSD. On the left-hand side, you can see us making rigid foams. And instead of doing it for construction, where the cost wouldn't be efficient at the moment, we made them into rigid foams for surfboards. In the middle thing, we made soft foams. These are foams that might be used in seats, but you can see that we can manufacture them with lots of different colors and so on and so forth. And in the micrograph there, you can see sort of a blow up of the cellular structure of these things, and this is what makes them so soft. And then on the right-hand side, you can see our latest project where we're making polyurethanes elastomers so that we're making renewable flip-flops. Now, these renewable flip-flops, are sort of the unofficial shoe of Southern California, but it's also important for the 8 billion people on our planet, the 2 billion people at the bottom, their chief form of footwear is a polyurethane sandal. The current ones do not biodegrade, so when the strap breaks off or there's a tear in the sandal, then they're just trash, which lasts for forever. These sandals would be biodegradable and renewably sourced. I want to thank you very much for your attention, and I hope you have a good day.